here is just a good mind map for you to see what are the conversions of the acid derivative. So from the COY, the coil company, you can add the alcohol, you get the ester. We call this step alcoholysis. You throw in some form of amine. Here we are using ammonia, you get the amide, aminolysis. You throw in a hydride equivalent, maybe from lithium aluminum hydride, sodium borohydride. Then you get the aldehyde. And then second step, alcohol. You see the reaction doesn't stop here because you are using a very fantastic reducing agent called lithium aluminum hydride that will give you a lot of armory of hydride equivalent to attack any CO double bond. Now when you throw in some Grignard reagent, it will be a nucleophilic substitution first step, and after that, of course, this is not a living group, so more of this will attack again. You have more bullets to shoot at this bond, and then you get the alcohol. Try to compare, right? Not isolated here for the intermediate. When you throw in water, it will give you a carboxylic acid called the process is called hydrolysis. So how do we make the acid halides from carboxylic acid? We use something called the thionyl chloride. Let me spell it for you. Thionyl chloride, SOCl2. Now whenever you see thio or thio, some people like to read that way, in organic chemistry, organochemistry, we know that it must have some sulfur inside. Sulfur. When we want to change it to the acid bromide, we throw in PbRO3, phosphorus tribromide. That's the name. Alright, in the presence of ether as a solvent. But we know that this is rarely used because it's not that stable itself. It's still reactive, so it's very hard to be controlled in a reaction. Like when the reagent is so reactive, it doesn't discriminate against any reagent, it just react and quickly kill itself. It will just kamikaze and do a suicide because itself is so high in energy. So it's bad for us because we want this reaction to go through, but sometimes the reagent is so reactive that you just pick anything that can react and it's gone. No more. And that's good game, right? Now how do we make ester from carboxylic acid? We can do this via carboxylate anion. It is a simple SN2 reaction with a carboxylate anion of a primary alkyl halide. So we are using this as a nucleophile, although it's quite weak, but it could still happen. Lone pair attack the carbon, that's delta plus of an alkyl halide, take out a good living group called iodide, and then we generate the ester. Here we see a very good yield of 97%. It's perfect. Alright. Some people may say, here, come on, the oxygen lone pair gets delocalized over to this oxygen, so the negatively charge is not actually very powerful. Yes, you're right, this is a weak nucleophile. But the thing is, it's a weak nucleophile, but the thing is because this is a primary alkyl halide, and you're using an iodide as a living group, so it could occur. So beware. Only primary alkyl halide could be kicked out by a carboxylate anion. Here, we can also use an acid catalyzed reaction. We call this a Fischer esterification, one of the main reactions in the synthesis lab for the chemistry major. They have to do it and make some fragrance in the lab themselves, and it really smells good. Fragrance. What happens is you add the alcohol equivalent to form the particular acid that you need. In the presence of a strong acid like HCl or H2SO4, it should be of a high concentration because it catalyzes the reactions. We use the excess of the liquid alcohol as a solvent as well. Like you add this in yellow to be more so that it dissolves everything here. Alright, but this synthesis is only limited to methyl, ethyl, propyl, and butyl esters. So if you want to form a pentyl butanoate, it's not very good. Now here on the right side, you see the mechanism. So step 1, this lone pair of electrons on the oxygen of the CO double bond pick up the H because this H is polarized by the chlorine that's very electronegative. So this is delta plus, it picks it up. Now the O forms 3 bonds, that's why it takes a positive charge. That means that now this carbon is very electron deficient because it has a plus charge next to it. So alcohol, even though it is not a fantastic nucleophile, can go in and attack, and then it breaks the pi bond. Same old story, you get a tetrahedral structure, which is very crowded, so you prefer to give way. And you reform the pi bond and kick out the other part. You see, here is all equilibrium. Now don't tell me that, right, because it's all equilibrium, that means you can start from here, you get this, then goes back. What it means is, yes, it is a two-way street. It can go and form 2, and then once you reach 2, 2 can become 3, and 3 can become 4. Right, so what do we do to enhance the yield? This is what we want to get. So immediately after reaction, we will just do a distillation. So we get rid of any products that we get instantly. And so this is gone, and then now, 3 wants to become 4 because there's no 4 left. This is equilibrium, so you just drag everything down and eventually form more of the product. Now this is a much better way to form an ester. We use an acid chloride, most reactive, okay, because it's so reactive, that's why the reaction is complete. So here we have a chloride, which is a fantastic leaving group, nucleophile coming from alcohol, which is okay, just ordinary. It will form the ester, close to 100%, very high yield, and somehow it is a full arrow. What if we are given the starting material to be benzoic acid, which is a white compound, white powder? We can first make it into the acid chloride, benzoyl chloride, by adding thionyl chloride here, and then we add the alcohol. Or some people will just say, okay, I just throw in the alcohol and boil in H+. But the thing is, this is not a good reaction. This is reversible, right? So to summarize this page, direct nucleophilic acyl substitution of a carboxylic acid is difficult because the OH group of the acid here is a poor leaving group, so it doesn't like to go away. But the reactivity is enhanced by protonating the carbonyl oxygen to make it more electrophilic, then this one can attack. Now some people say that, oh, if I can do it that way, then why don't I do a doping? I do a similar reaction, but now I'm using a base, right? I should get an amide. But the thing is, because we know that amines are basic, so it has a lone pair here, and carboxylic acid is acidic, so it will prefer to undergo a simple acid-base reaction instead, and that means you get a salt. You get a salt. So this effort is very futile because you don't get a real covalent bond that connects the carbon here and the nitrogen here to form an amide. So this is not good. So what do we do in the lab is, first we convert the carboxylic acid into a big group here called DCCO. So we use the reagent called DCC, stands for dicyclohexyl carbodiimide. Dicyclohexyl carbodiimide. Now you see, when it joins, right, this part becomes a huge leaving group. It becomes a fantastic leaving group. So when your lone pair on the nitrogen of the amine comes in, it will attack and kick this out, and it will join. And you get dipeptide here because the lone pair of the nitrogen came from an amino acid. So here you get a product coming from this reaction. Success! So for acid chloride, which is one of the most reactive acid derivative, if you throw in some ammonia, of course you're going to get the amide form, because this one can attack and kick out the good leaving group chloride, which is a very weak nucleophile. Throw in some alcohol, you get the ester. Throw in some carboxylic ion, acid anhydride, water, you get back the carboxylic acid. So because they're so reactive, you can throw in water, you get back the acid themselves. And this is the mechanism I've spoken just now. It's all similar. This part again is very similar to the acid chloride that I've talked about. In the same manner, the lone pair here will attack this carbon, kick out the chloride. This is mechanism, and you get a very high yield of the acid anhydride. Right? All these are very similar. Try to see and a pattern, an analogy. So you dope it. Now what is the purpose of this slide? You see, acid chloride reacts with alcohol to form esters. We know that, right? Now reaction is carried out in the presence of pyridine, which is a base, or NaOH, which is a base, to react with the HCl that's formed. Because we know that after this reaction, this Cl goes with the H. So your byproduct here is actually white fumes of HCl gas. Very harmful, hydrogen chloride, toxic to us. We will get breathing difficulties if we inhale some of these. So we throw in the solvent, a solvent called pyridine. Pyridine can also act as a base itself, so it's lovely. It can just absorb the HCl that's generated. Now the reaction here is strongly affected by steric hindrance, which means to say that if you have some bulky groups on either side, it will slow down the reaction very much. So it's possible to esterify an unhindered alcohol selectively in the presence of a hindered alcohol. Now this is a good example to show you what happens here. In the same molecule, you have two hydroxy group, two alcohol group connected to the same molecule, and they throw in one molecule of the acid chloride. Which one will attack? The blue one wins, because blue one is actually a primary alcohol. That means it's less hindered and more reactive. This is secondary alcohol, the pink one, more hindered and less reactive. So the more reactive one will win and goes in to form the ester here, not there. So we learned that acid chloride reacts with amine rapidly to form the amide. Most common laboratory preparation of amide using mono-substituted and di-substituted amines. Remember, tri-sub cannot be used. The reason is because you see that for here, simple amine with acid chloride, we are doing a condensation reaction. Condensation, Cl comes off with the H from here, right? But if we have a tertiary amine and R3, there isn't any H attached to the nitrogen, so it cannot come up with the chloride, and that's why there's no reaction. Now because HCl is formed during the reaction, two equivalent of amines must be used. What it means is, right, normally we know that it reacts stoichiometrically 1:1 ratio, but knowing that the byproduct is HCl, we know that any base present here would react with the acid very completely. So when we spam a lot more, some of it reacts with this to form that, and some reacts with the HCl. So we will salvage a lot of my product. We won't have a low yield. This is good. First equivalent reacts with the acid chloride to form the amide and the HCl. The second equivalent reacts with this byproduct to trap the HCl to form the salt. Alright? So some people ask, what if we do not use two equivalents? What happens is, when the first half equivalent forms with this, I get the amide, and then I get half of HCl, and then this half reacts with the other half of amine. That means here there will be excess, and it is quite wasteful because I try to finish off my reactants. This is the one that's more expensive and more limited. This is a bit cheaper and it's easier to get. Now acid chlorides are reduced by lithium aluminum hydride, a very good reducing agent that I've mentioned before many times, to get primary alcohol. The reason is because first step, the hydride equivalent goes in, kick out the chloride, you get the aldehyde, but we know that it won't be isolated because this can be further attacked by the second form of the hydride, and you get back the primary alcohol, because you know aldehyde, when you reduce it, you get primary alcohol. Grignard reagents react with acid chloride to form tertiary alcohol, which two of the substituents are the same. What it means is, you put 2 moles of these, and the first one goes in, kick out the chloride, nucleophilic substitution. Then it doesn't stop here, because you still have some Grignard reagents that can attack and do a nucleophilic addition, and you get an alcohol product.